Ladies and gents, thank you so much for coming. It is fantastic to see such a large audience. And we chose to be in this lecture venue, just in case you wonder why we decided to squeeze you all in here, is because we really wanted to record the talk so we can post it on the internet later on. So for those of us geologists that couldn't be here, they can watch it later on YouTube. So that's why we all squeezed into this room. But I've never seen this room so full in my life before. So thank you all for coming. Tonight we have a very, very special talk which sort of precedes a very special field trip to Barberton, which is happening next week. And so for those of you who aren't going on that field trip, this is a really excellent opportunity to have a prelude to all that interesting science that we're going to see next week. It's an interesting year because there are 3 50th anniversaries this year. There's the moon landings, the Apollo moon landings, there's the discovery of Komatiites, and it's also Richard's anniversary, wedding anniversary. So there are 3 very important anniversaries. So I'd like to just quickly introduce Maurice and Richard, who really don't need an introduction, but both are Wits MSc and PhD graduates. So that makes us very proud that we have our alumni back here to present this very interesting talk. Together they have over 60 years of experience in the minerals and exploration industry. Richard worked for 15 years in goldfields and has been since then developing many, many economic mineral commodities throughout Africa. Maurice worked at JCI for a similar amount of time and then came to lecture and was eventually a professor here at Wits and set up a center for mineral and exploration. And both are now advisors and founders of VM Investments and are continuing to develop fantastic mineral resources throughout Africa. So thank you so much for offering to give this talk. It is wonderful to have you here, and thank you all for coming, and also to the sponsors for the drinks and the snacks that you'll enjoy later, both to Bushveld Minerals, to the School of Geosciences, to Chimera, and to the GSSA, as well as the Egoli branch. Thank you for sponsoring the talk. And to the YouTube audience who will be watching this in the future, welcome and thank you. And over to Maurice, or Richard.
Good afternoon, everyone, and it's a great pleasure for Richard and myself to be here to talk about Komatiites. Both our careers started here way back, in fact, in 1958. And in fact, also the Komatiite story started here back in 1965. So I'm going to run through an introductory bit to the whole Komatiite story, and Richard will follow up with a follow-up talk as well on the same theme. So how it came about was that in 1965 there was an international upper mantle project, and South Africa started taking part in that in 1965. The project started a bit earlier, and there were a number of projects, including, for example, eclogites and kimberlites and so on. But one of the projects was called Ultra Basics in Fold Belts. And it was realized there were some interesting ultra-basic rocks in the Barberton area, but not much was known about them. And so our mapping commenced in 1965, and in an area which had been neglected, the southern part of the Barberton area in the Komati Valley. And in 1969, we presented our results in Pretoria at an international upper mantle symposium, and Komatiite was then accepted, and it was a hitherto unknown class of volcanic rock, and it's of course named after the Komati River, which flows through the type locality. Okay, so subsequent to that, Komatiites have been found in many areas, but in South Africa there is Barberton, and also in the Murchison Range, Komatiites, and Guyani as well, and even in the Petersburg belt, but also down here in Commondale. And Alan Wilson is here, and he's done a lot of work on Komatiites in Commondale. Some pretty interesting stuff has emerged there. So as part of the geological legacy in Barberton is very important, to the extent that Barberton has been created as UNESCO proposed and now accepted as a UNESCO World Heritage Site. A lot of it, as I say, based on the fundamental importance of its geology. And some of the important geological factors that have exist in the area that have resulted in this UNESCO thing is you've got evidence of the earliest Earth crustal development, what happened 3.5 billion years ago. And as part of that, of course, the world's oldest and hottest lavas, Komatiite, they were forming then. The presence of the earliest life forms also occurred. Komatiites, as we'll show now, have a remarkable correlation with gold mineralization. And it's also the first granite-forming continental crustal activities was beautifully exposed in the region. There's evidence for early meteorite bombardment. And in the sediments, there are sedimentary structures which give clues to the early Earth processes along the Makonja, really recently established Makonja Geotrail across the central part of the Barberton mountain land. So the state of the game in 1965 was like this. We had volcanic rocks were mapped down here in the south, but in no detail, just a general idea. There were some pillow lavas and there were some volcanics, and they were just lumped together as the Onverwacht series. It was known there were some differentiated bodies, but there were also a lot of talc schists and amphibolites and a whole lot of rocks which were quite difficult to interpret. And they were all lumped together in what is called the Jamestown Igneous Complex, shown in the cross-hatching over here, including down here in the south. And these rocks were considered to be co-magmatic with this granite here called the Karp Valley granite, almost a similar idea to the Bushveld complex and the Bushveld granite. As a result of the work, and incidentally, our mapping essentially covered in detail a large area in the south down here, and also a pretty large area up in the north. Those are the two key areas that we covered in our mapping. And as a result of that, it's emerged, of course, that there were a lot of rocks of ultramafic type, now called komatiites. They are shown in light mauve here, and they occur all the way around the Barberton area. And in addition, there are a number of layered igneous complexes along the northern flank here in particular, and they are, as we will show, differentiated komatiite layered complexes. Now, one of the reasons for the southern area mapping was the phenomenal exposure, and you can see and the rugged nature of the ground. This made mapping pretty difficult. And here's the Komatiite River running through the area. And you can see some pretty high hills in the background. So this here, however, is the type section of what became known as the Komatiite Formation, where these komatiites are best developed. And you can see from this Google image how classically layered and exposed the sequence is in the type section. One point to add is that we spent 4 full seasons doing mapping here, detailed mapping. It was possible in those days. These days, I mean, virtually no mapping is done. However, it was really this mapping that resulted in the discovery, as we'll show you. And this is the detailed map that emerged. And we divided, and this is in the type section. This is a locality called Spinifex Stream. But in any event, at the base we have what is called the tear-sprayed formation. We distinguished that, characterized by felsic tuffs interlaid with komatiitic type lavas. We then have the Komatiite Formation, which is this here, and then we have the Hoogenoeg Formation, and they're all pretty significantly different, particularly the Komatiite Formation, which we'll talk about. It's a series of essentially, we found pillow structures, basaltic pillows in the green-colored material here, but interlaid with it were these peridotitic rocks, which had us pretty well baffled because we thought they were possibly lavas, but at that stage, no ultramafic lava was known. So these are the basaltic pillows that you find in the associated rocks, and they are classically developed pillows with, in fact, these downward protuberances here, which indicate younging direction, and the chilled margins, altered chilled margins, etc. Classical pillow structures, unequivocal subaqueous extrusion. And they interlayered with these peridotites. So what do the peridotites look like? Some more pillow lavas, classically developed. The field excursion will visit this locality, incidentally. And all sorts of textures like these variolites or ocelli structures which occur in pillows. I won't go into any detail. And then these quartz veins which occur in original gas cavities near the top of the pillows, indicating younging direction very clearly. And then in this basaltic rocks also the strange structure, which later turns out to be Spinifex. It's a crystalline kind of a quench structure, we called it. And you have both orientated and random blades of essentially original clinopyroxene, now altered to actinolite. So we then had a close look at this particular area here. This became the type section for the Komatiite Formation. So we'll zoom in here. We did a lot of work in the stream down here called Spinifex stream, where you have almost continuous exposure and where you could really see the field relationships very clearly. And really simply put, and this is a bit schematic, we have the basalt shown in green with the pillow structures that I showed you. You then have peridotitic zones shown in that darkish mauve, but then you also have these broad zones with multiple little mini ridges of peridotite, but then in between some pretty interesting textures. And so there are three of these major zones occurring. So this is where our detailed study was done in Spinifex stream. And if you look at those broad zones, what you see is that there are these little mini ridges. There's one there, over there, a little one over here somewhere, there. They're very insignificant looking, but they're pretty important, as I'll show you now, because those actually are the basal parts of these, what have turned out to be flows. This part over here. But in all cases, the basal part passes up via a zone of more or less parallel orientated olivine crystals. These are mainly olivine crystals, incidentally, so classical peridotite with clinopyroxene. But then it passes up into this strange texture, which we would call a parallel or plate spinifex. This is eventually called Spinifex structure, named after a spiky Australian grass, which it resembles. And that in turn, every time passes up into random Spinifex. So that sequence, wherever you find komatiite lava, you're going to have that sequence. And so these are various flows, basal part Spinifex, basal part Spinifex, and some flows, like Richard's flow over here, is only about 30 centimeters, basal and upper Spinifex. We studied that one in detail, but we've looked at all of these flows over here. Each of those is a flow. And from that, we started getting some interesting evidence there, incidentally. I'll go back to this other one. This one here, this specimen belongs to Tinus Kluter from the Council of Geoscience, and it's on the table over here. It consists of the bladed Spinifex. Well, at the base, in fact, is basal olivine-enriched peridotite with quite a lot of olivine, and then the bladed Spinifex passing up into what we call random Spinifex over here, and then into a kind of a broad chill zone, but significantly right on the surface. You might be able to see it here. It's a very thin sort of crust of what we think is a kind of a pelagianite, very fine-grained glassy material. And examples of the Spinifex, here you can see bladed to random, quite classically. That's invariable, in fact, that's succession. And then under the microscope, some amazing geometric shapes. These are serpentinized olivine crystals over here. In between, you get tremolite and some magnetite, also pretty well aligned. So amazing crystal forms, geometric forms. But in the basal zone, this is however, quite a rare sample. you get essentially a olivine which is accumulated slightly. These zones have magnesium enrichment compared to the Spinifex. And in this case, the olivines are beautifully preserved with only minor serpentinitic alteration along some, and in a ground mass of essentially original clinopyroxene. And then at the top, although we didn't really find any pillows, we did find these structures. Here's the top chill coming down, and it penetrates into the upper part of the flow, and it seems to surround these areas here. And these we might call pilloids, perhaps. They're trying to form pillows, but this the top chill here is very important. And then the other thing that we came across was this cross-cutting dike of peridotitic composition. You can see it cutting across a pretty large dike. And that terminates, let's see if I missed something here. This is further evidence that there was a peridotitic kind of a magma. This was a feeder to some of the upper flows of komatiite. I'm just going to escape there. Yeah. And then on a smaller scale, we also found these zones of serpentinized peridotite. Also evidence now that there was this peridotic magma around. And then shortly after our work, komatiites were actually discovered in Monroe Township in Canada, who defined this texture more precisely, a guy, Dale Pike, in fact, in Monroe Township. And comparing those two is just a remarkable similarity in the overall development of a komatiite flow, even down to these chill things coming down from the top contact. So very consistent. And then we did experimental, we didn't, but we collaborated with Green and Nichols. It was actually in 1975, not 95. And they heated up a komatiite sample, and then they chilled it, and look what happened. Bladed olivine crystals and bladed and random olivine crystals. So that temperature, in fact, was over 1600 degrees centigrade when crystallization started taking place. So the crystallization temperature of these ultra-magnesium rich rocks was incredibly high, higher than 400 degrees higher than any other volcanic rock recorded. And from our work, we showed that komatiites dominated the lower section here, the Sunspruit Formation, the Tearsprate Formation I mentioned, and then the Komati Formation, all dominated by komatiitic basalt. And then, also occurring here in this anticlinal structure called Stainsdorf anticline. But then we also mapped out a very significant sedimentary layer here, and which we call the middle marker right there. And at that point, there was a dramatic change in the style of volcanicity. And from the magnesium-enriched komatiites, we passed into normal tholeiites. I mean, the lowest magnesium content of a komatiitic basalt is around about 11-12%. Tholeiites have magnesium content of 6-7%. So what happened in Earth history to give this dramatic change? There were still a few komatiites that took place, but in essence, there's a whole change in the style of volcanicity at that point, telling you something very fundamentally important about the evolution of the early Earth. And then when we plotted up the geochemical data, we found that in the Sunspruit Formation, you had the most magnesium-rich of the komatiites. So these are all true komatiites, or peridotitic. We call them peridotitic komatiite firstly, and now just called komatiite. Then we defined what is called a butt-class and geluk type, which perhaps overlap a bit, but mainly this would be geluk and this would be butt-class type. And then the pillows that I showed you normally occur in what is called the barberton type, but they're still pretty magnesium rich and depleted in aluminium basically. And then you get tholeiites, so there's a huge break here, and that corresponds to that middle marker again. And then you get into the tholeiite field, totally different to any of these komatiites. And then this is a plot here of magnesium, calcium, and aluminium. And this is the tholite field. Most of the, the rocks, similar rocks that you look at, all cluster in this area over here. But there's the Barberton type, the Botplaas and Geluk type is there. And this is the true komatiite, peridotite type komatiite, sunsprayed komatiite over there. And that sample there was also found 50 years ago. And where? On the surface of the moon. So that is another very interesting story. And here, another plot which actually shows a high calcium content compared to alumina of komateites, the blue field over there. And this is a feature of the Barberton komateites, high calcium alumina ratio. Other komateites subsequently found, they're still identifiable as komateites, but did not have such a high calcium alumina ratio. They were more or less close to 1, calcium aluminium. Most of the komateites have a great higher calcium to alumina ratio in the Barberton ones. Maybe it's got something to do with their age. It's about over 3.5 billion years, etc. We're not too sure. Alan would probably tell us something about that. And then this diagram here, the various plots you make, any plot you make, komateites always plot in a distinctive field, unlike any other described class of rock. And here's a simplistic kind of a diagram of komateites erupting, peridotic and basaltic, and then also with the intrusion here giving you these layered ultramafic complexes. In a primitive oceanic type environment, there might have been some granite around in places, but all evidence from the south area of Barberton indicates the lower komateites have been intruded by these early tonalitic type granites. So, bottom line is that if you look at rock types and look at grain size, you have volcanic, hyperbasalt, and plutonic. So you'd have a rhyolite, granophyte, granite, basalt, dolerite, gabbro, and now komatiite, peridotite, or pyroxenite, dunite. So it's a whole, it fills in this gap in the basic classification of rock types. And we presented our results. Incidentally, I should mention that we had huge input from a whole lot of pretty top geologists from all over the world, and a few of them are noted here. Professor Al Engel, Scripps Oceanographic Institute in California, Professor Preston Cloud, University of California, Berkeley, Mike O'Hara, Edinburgh, and then just before the Upper Mantle Symposium, Professor Harry Hess, we took down to Barberton. On the right, incidentally, is Carl Annenhauser, and that is Richard. Where's Richard? And this year is Harry Hess. And he was the fundi at the time. And he sadly passed away 3 months after this visit. But he was at the conference in Pretoria, and after presenting the talks, he was the first to get up because we'd taken him there, and he was pretty convinced about the evidence, and said, look, he'd been looking for this his whole career, in other words, extrusive ultramafic lavas, and he was very happy that he had now seen them, and so once Harry Hess had given the word, komateites were then accepted. And then they were widely found in all the ancient parts of every part of the earth. And then, just briefly then, on the north side you get these layered bodies. And I'll just briefly mention something about those because they are differentiated komateites consisting of essentially dunite and orthopyroxenite. And right at the top, maybe a little bit of norite and an orthosite, but very minor. These komateites are very depleted in feldspar. However, when you get concentration of olivines, you also get, and in structural sites, you get asbestos mineralization. He has an asbestos mine in the Kudu body. And in the background is the typical sedimentary core of the Barberton mountain land. So this is on the north flank, but just around south of Malalan. And there were some very significant cryostyle asbestos mines in the area. In fact, we actually, oh geez, what's happened now?
Sorry.
Oh,
Very good.
yeah, good. Thanks. So here is it is a major mine. We stayed there for about 7 months when we were mapping in this area. And this mine is on the Swaziland border. Swaziland border runs along here. It's called the Msoli asbestos mine. It's long since closed down, and sadly the whole township has deteriorated. But it was, asbestos became a dirty word, as you know. This is, however, chrysotile asbestos, which is not as bad as prasidylite. There's some of the chrysotile veins in serpentinized dunite, differentiated komatiite magma. And then in the northern part, some classical layered bodies, the Ship Hill and the Butt body over here. On our excursion, we'll stop over here and have a quick look at the basal dunite. So you have dunite, orthoperoxenite, and right at the top, a little bit of norite and or gabbro and anorthosite. But then you've had a lot of surface weathering, and all the blue areas here are magnesite deposits. So they've been derived from superficial alteration of the dunite to form a thing called berberite, named after Berber in Ethiopia. And it's essentially the oxidized weathered product of a dunite in which the magnesium is concentrated to form veins. Incidentally, this here is it's only about 1 meter or 2 wide, but that's right at the top of one of those layered bodies, in north acidic. And this here is an orthoperoxenite. But this is what the secondary magnesite looks like, and it's still being mined in the Malalan area at the moment from the basal olivine accumulation in the dunites. And then here's a simplistic model of what happened next, and that was the invasion of that early komatiitic oceanic type crust by these very distinctive tonalite and trondhjemitic or leucotonalite granites. And they incorporated all sorts of pieces of the komatiite to form xenoliths, often aligned with a strong gneissic fabric. And this type of relationship is beautifully seen in the southern part of the Barberton area, and it was mapped pretty in detail by Prof. Carl Anhauser and Lawrence Robb. And here you see one of those contacts with these are komatiitic basalts with a complex interaction between the gneiss here and the komatiite to form a mixed rock, which we call a migmatite, contact migmatite. And this is where we use the 2 papers that was presented and published that announced komatiite, the geology and geochemistry of the lower ultramafic unit of the Onverwacht group and a proposed new class of igneous rock. And this one here, evidence for the existence of a mobile, extrusive, perioditic magma from the Komati formation of the Onverwacht group. Those are the 2 papers that talked about komatiite for the first time. And subsequently, all sorts of publications have appeared. The first one here was 1973. The comments of a book here, edited by Nick Arndt. The discovery of komatiite, ultramafic volcanic rocks, is one of the most important petrological advances of this century. And more recently, another book by Nicholas Arndt on komatiite. And literally hundreds of papers have been published. Komatiites have been found all over the world. And it's a huge topic of research as well. Just to show you an example, also the other mineralization komatiites is nickel, and this is Zimbabwe. The rock shown in blue here, all komatiites, overlain by tholiites, very similar to the Barberton story, lower ultramafic unit and then tholiitic basalts. But a significant nickel deposit was found here we found this in JCI in 1970. And over here, the Damba and the RT deposits in komatiite flows. And then most recently, komatiites have been found in China. And here, we did a visit. We were visiting some geoparks. This is the Mount Taishan Geopark in China. And we were treated like royalty over here at this museum, which they just established. That's Richard, and that's myself. This is Alma Fanika, who's coming on our excursion to Barberton. And And in fact, they made a huge thing of komatiites to the extent that the main frontispiece as you enter the museum is a piece of Spinifex textured komatiite. And this is the so-called Geological Museum of Mount Taishan Geopark. Right, I think now that is my talk, and I think now Richard's turn to say a few things. Okay, thank you.
Okay, well, I'm sure you all komatiited out after that, but I'll try and be as brief as possible. So the view you're looking at there is the Steynsdorp Valley, and we'll talk a bit about that and the significance of gold mineralization in komatiite. However, before we do that, a brief look at the tour that we will be doing shortly. The various stops are marked over here. We'll have a good look at all the pieces of evidence that Morris talked about. Up here, the Steynsdorp Valley over here, and then to the northern flank where Trevor Pearton will tell us about komatiites, an area mapped by Mike With, who's in the audience, of komatiite flows and also differentiated bodies in the Agnes mine area. And then we'll have a brief look at the Maconjwa Trail, just parts of it, and then up through and have a look at the layered body up here, the Carp Maiden body that Morris talked about, and then have a look at some of the granites here that were mapped by Lawrence Robb. And just at this stage, I'd also like to thank the people who have collaborated in putting this trip together, which has been quite a daunting task, and also the people who are going to accompany us. That'll be Professor Lawrence Robb, Professor Carl Anhauser, Dr. Pearton, and also particularly the Egoli branch for having the will to organize a trip of this nature, and particularly Taryn Scharf and Andries Puerta. So a lot of work and planning have gone into this with the local people in Barberton. Tony Farrer, who is the chap who established the Maconjwa Trail, and Roland Jones. And these chaps are absolutely passionate about Barberton, and also passionate about telling people what this new World Heritage Site is all about. And as Morris has said, it's all about geology, or mainly about geology. Now, just reverting back, and I'd also just like to thank Grant Bybee as well for suggesting this talk this evening, and he'll also be on the trip to Barberton. Morris talked about the lower formations and the middle marker. So I want to talk briefly about that middle marker. When we started off our work, we started mapping where the best exposure was, which was in the Hooggenug formation. That is that green formation. There was no map that looked like this. This all evolved later from the mapping, and mapping was fundamentally important. And standing on pillows right here on the Hooggenug with Prof. Al Engel, and this is in 1966. He, in fact, had been busy at the Scripps Oceanographic Institute dredging basalt from mid-oceanic ridges, from sea plateaus, from volcanic islands, and so on. And those basalts were all turned up very, very similar characteristics. That is, they were low potassium tholiites. So Engel was pretty pleased to see low potassium tholiites. He'd been looking for them, and he thought that they should exist in these early greenstone belts. However, Engel, standing on these low potassium tholiites, said, look, if you walk down in the stratigraphy, you may find even more primitive rocks. And he called low potassium tholiites pretty primitive at that stage. And so he was absolutely right, because these are the komatiites. Anyhow, that's another story. And we had with us on that same trip another guy called Preston Cloud. And his interest was not in volcanic rocks at all. His interest was in sediments and the origin of life. So we had these two people with us, and we took them around for probably a couple of weeks, and they visited us again later. So we had great interaction, and their input was fantastic. And so what we find is that within the lower sequence of komatiites that Morris described, the Sunspruit, Teerspruit, and Komati Formation, which emerged after the mapping. In fact, Engel and Cloud never really saw the final product. They retired, and they both are dead. However, in all these formations, there are various sedimentary layers. They are often quite narrow, and sometimes between lava flows, and sometimes act as the conduits for the emplacement of the differentiated sills that Morris talked about. So the sediments are interesting because they do contain signs of very, very primitive life. So if we have a look quickly, this is an example from the work of Carl Anhauser, where you're getting banded iron formation, grunerite chert rocks with a Spinifex textured peridotite komatiite, and a banded iron formation at the top with some basaltic komatiite, and then another cycle. And those are very well preserved in the Skarpenberg belt, suggesting again and confirming the volcanic origin of these Spinifex flows. And we'll be visiting that site on the trip to have a look at these rocks. That's what they look like. A banded chert, which is the light-colored material, and this grayish-colored material over here, which is essentially grunerite from an iron-rich sediment, so banded iron formation, basically. As we go up into the Teerspruit formation, we have interlayered there a whole sequence of felsic volcanics, and these are probably the first sign of felsic volcanism. Felsic pyroclast, you can see graded bedding, and you can see different clast sizes, but you can also see, very interestingly, these black bands over here, and those in fact are black banded cherts. And we took many people to look at these things and were sampled, and they claim that they have found life in these, and signs of life, etc. And this is one of the very first, earliest guys who came out. His name was Keith Van Volden, and he was from NASA. And that was about 1967. So just before the lunar landing. And you can see the nice black chert. This was in the Teerspruit formation that he sampled and took back for work on lunar rocks and so on, and to compare lunar and other rocks. So he was one of the first ones. There, incidentally, is the middle marker, and I should just move on quickly, and the middle marker separating, on the left, the sheared komatiitic basalts over here, and above the middle marker, beautiful, beautifully preserved pillows. And as Morris said, there's a huge break in volcanicity, style, and so on at this middle marker position. It's a fundamentally important break. So that's what the sheared komatiites look like. This is actually in the Steinsdorp Valley, which we'll come to very briefly now. And that's what the tholiites look like above the middle marker, beautifully preserved pillows. So very contrasting chemistry. That there then is the middle marker over here, and these are the Komati formation, and then a whole bunch of cycles within the Hooggenug formation. So you get a cycle of tholiite capped by a chert, cycle of tholite with alteration and chert due to hydrothermal activity on the sea floor, and more cycles, and eventually a huge zone of acid felsic pyroclasts capped by more cherts and sediments, and then abandoned iron formation. So a beautiful sequence there of cyclical volcanicity. And here's one of the cycles. This here would be an altered komatiite, hydrothermally altered, and this would be a chert at the top of a cycle. And you can see, you can follow that chert. There it goes right the way through the top of a cycle. There's another little cycle over here. All volcanic cycles, but they're all tholiites, not komatiites. This is now in the Hoogenoeg Formation. And then at the top, this clastic rock I was telling you about, the pyroclastic fragmental rock, there it is, with beautiful flame structures. There's a good one there, etc. And here is the banded chert again at the top. And then even higher up in the sequence is more carbonaceous and cherty material. This is in the Kromberg Formation. And this is Preston E. Cloud Jr. sampling that chert, 1966. So the whole story of looking for life started way back, and a huge number of papers have been written on the topic. However, a recent paper has highlighted and has summarized all that previous work on how you recognize ancient life forms in sediments between various lavas. And one of the there's a meteorite bombardment with a meteorite fragmental rock, which is another story. But what they found recently are these biomats. Now, interestingly, these biomats are very well preserved in that middle marker, and that they fit in with that very important break that we talked about, with the lower komatiitic dominated materials and then the tholiites above, and in between, this is what you find, these organic biomats, and you can see how they've been disrupted by sedimentation there, and you can see over there how sedimentation is and these, according to the authors, but I think according to many others, are the first unequivocal sign of life in the Barberton area and in the world, the oldest life, about 3.47 billion years old. Okay, but then the middle marker has other uses, and that is you can follow it around the Onverwacht anticline through there, major fold structure, and then it reappears in the Steinsdorp anticline. The other thing I want to point out is the occurrence of gold. Now you'll see here that all the little yellow dots are gold prospects and little old mines there, some over there, and right around the Steinsdorp anticline over here. But that is a remarkable pattern. Most of them are in and around the middle marker. So we then did a detailed study to see what was going on, and this is the Steinsdorp Valley, and this was a thriving mining community in the 1880s, just before the discovery of the Witwatersrand. In 1967, there were still some old relics, a 3-stamp battery over there, and the old the Gypsy Queen mine over here with the cemetery, the Steinsdorp Cemetery. This here, for later reference, is a porphyry body and intruded into komatiites, but with a gold quartz vein running up there where the vegetation is. So what is going on? There we get to the middle marker again, and I showed you the nature of the rock below the middle marker, and the nature of the rock above the middle marker is the tholite, the important break that we're talking about. And then right above the middle marker, some very interesting things happen. The middle marker is somewhere over here. This is a massive tholite over here. It's jointed, the dip is quite steep, but this is a sequence of pillowed tholite over here. But and the middle marker itself is somewhere here, and the actual komatiite sequence is being more prone to erosion, is in the valley down here. But I want you to look at this. You see, this here is a quartz vein. So you can see that that is gold bearing, and this is the so-called Fullerton Creek, and that was the mainstay of gold in the Steynsdorp goldfield. So if we look at the Steynsdorp goldfield, we find our old friend, the middle marker over here, and this is an anticlinal structure that has been, the nose has been faulted. So the Hoogenoeg formation is the light green. What I want you to notice is there is a fault over here, through here, and the red are quartz lodes, and you can see there's a whole plethora of little mines. They've all got fancy names like Gypsy Queen and Mother of All, etc. Right here is a major alluvial working called Fullerton Creek, and that photograph of the middle marker is taken right over there. And it looks as though, and we think, that all this alluvial gold, and that was the mainstay of Steynsdorp. Steynsdorp itself was situated somewhere here on the Londozi River, was derived from these quartz veins with gold along the fault. But if you look at the middle marker, you'll see that virtually all the mines here in the nose occur just above the middle marker. There they are, over there. And here on the east limb, you'll see them over here, the Idaho, the Boar's Head, all of them, right, just above the middle marker. You'll also notice that the dikes kind of terminate at the middle marker, or the outcrops of the dikes over there. And you'll notice that the Gypsy Queen mine over there occurs in that competent porphyry that you saw earlier. So what's going on here? And we think what happened was that this is the Komatiite formation. These are the felsic tuffs that you saw in the Teerspreit formation earlier on. And we think that at this time break, this hiatus over here, you got hydrothermal seafloor alteration, you got the development of pelagianitic tuff, and work has shown that many of these funny sediments that occur at the top of the Komatiite formation, and in fact, komatiites themselves are enriched in a number of elements, gold being one of them. So it looks though what has happened is that the gold has been liberated from this material over here below, just below that middle marker. With metamorphism and various stages of mobilization, the gold eventually has moved down a geothermal gradient and been deposited in suitable structural traps within the more competent rocks of the tholeiitic type of the Hoogenoeg formation. And looking at all the gold mineralization in Barberton, and Trevor may comment on this further, that's where the origin is, from komatiites, right there. But then it's been mobilized and placed in suitable structural traps. The other interesting thing is that it looks as though the nutrients that developed towards the top of the Komatiite formation here, which is this center of the anticline, was full of nutrients. And we mentioned some of them. And those nutrients were what you needed for life. And that's why you get biomats developing in the middle marker. So, komatiites have played, we think, an extremely important role in all sorts of things here, and particularly the interlayered sediments of the komatiites. Anyhow, that's the story of the Steynsdorp goldfield. The gold deposits on the northern flank, I won't go into. Those are the real big mines, and this is the Tevreden green schist belt, which Trevor Pearton was talking about. And what you find here, the light blue is a major complex of spinifex textured basaltic komatiites and peridotite komatiites, as well as layered sills of komatiite. But interestingly, it's cut through by shear zones, which contain carbonate alteration, the development of fuchsite, and significant gold deposits. And you'll notice that all the gold deposits are along these carbonate altered zones that occur in this in this pioneer complex of komatiites. So again, komatiite's relationship to gold here is quite a compelling one, and I won't go into detail of that, but a new stratigraphy has been established. This is the belt that Mike Wits mapped. I'm not sure if you'll concur with everything I'm saying, but it would be interesting to get his comments. This is the new type section that has been developed over here, which includes Spinifex flows, etc., as well as layered, slightly differentiated sills of komatiite. And there's the stratigraphy. I won't go into that. And looking at some of the mines on the north flank of the Barberton Belt, some of the bigger mines, this is the famous Lily mine. And what happened here was that we have a major fault running through here, which separates komatiite, this is all komatiite over here, of the Geluk type, high magnesium, from fig tree rocks here to the left. And it's along this boundary that you've got the emplacement of the quartz lodes. And incidentally, that hut over there was the one that went down in the Lily mine disaster. And they're still trying to get the people who went down with it. So the komatiites there are very obvious. And then if you look at the Sheba mine area, all the major mineralization is associated with these very tight anticlines of komatiitic rocks, which have been folded and structurally disturbed, and also they occur along the contact between the Moody's rock over here and the fig tree over here. And you can see that some of the gold is now migrated into the Moody's, which is more competent again. So it's a matter of a source rock and a competent rock which will trap the gold. And that seems to be the pattern. And if we look at these things, you'll see there is a tight anticlinal structures. You can see them over there. So if you like, that's a little Stainsdorp anticline right there, with the gold coming up through here. These are all komatiites through there, and being deposited there in suitable structural traps, and being deposited here in structural traps, and being deposited here in a competent fractured Moody's quartzite. This, of course, is the famous golden quarry and the cathedral stope at the Sheba mine. So again, a very, very close association with a komatiitic source here. And that's just a section to show a longitudinal section, again showing these steep anticlines of komatiite, altered komatiite, with reefs in the hanging wall here. But interestingly, as soon as these reefs enter the fig tree, they pick up arsenic. So these are mainly arsenical ores in the fig tree. So now, flying a very, very big kite, where did all the gold in the Witwatersrand come from? And if you look at the mapping of the Johannesburg granite dome through here, that's all granite, tonalites, similar age to Barberton. But this material here are huge komatiitic ultramafic complexes. You can see them here and here. These were mapped by Carl Anhauser. There's another one here, the Modderfontein complex, containing significant amounts of komatiite. There are a couple of little gold showings around, but the important thing is that we find in the Witwatersrand conglomerates over here, the gold in the conglomerates must have had a source. We think now that the only source possible were these komatiites. you've got to obviously stew them up by granite intrusion, as we've shown here in Barberton, and mobilization, and then you've got to erode those veins to give you a placer concentration. And it looks as though there might have been a major belt of komatiitic rocks running around what's now called the Rand anticline, and most of it's now eroded. These are the roots of the source of the Witwatersrand gold. And some of the work now, people have done work on the Modderfontein complex, and they found important chromite pods and layers. Now, I did my MSc on the mineralogy of the Witwatersrand reefs, and one of the things that was always interesting was the occurrence of chromite in those reefs and the occurrence of platinoids, osmiridium in fact, in the Witwatersrand. So where did that come from? It must have come from an ultramafic rock. And what kind of ultramafic rock is there? Only komatiite. Here it is. There it is. So maybe that's why we got, the world's biggest gold field right here. Anyhow, that's another story, and a big line of research now to compare the heavy minerals in the Witwatersrand with the chemistry of similar heavy minerals in the komatiites of these komatiite complexes in the Johannesburg Dome. So there are all sorts of implications and all sorts of new lines of research here will tell us something more about this very early significant gold mineralization in our planet, which we think is related to komatiitic magnetism. So that gives you the link now of komatiites with early life, with gold deposits, with nickel deposits, which we haven't even mentioned yet, but that's another story, all in komatiites. All the Australian nickel deposits, Kambalda and so on, are in komatiites with flows similar to what we've seen here in Barberton. Anyhow, that gives you some idea of some of the thinking behind the discovery of the komatiites and the significance of komatiites, which has been developed by numerous workers over the last 50 years. So yeah, thanks very much.
Maurice, Richard, thank you very much. That was a fantastic, fantastic talk. And I think we can all give another round of applause for a really interesting talk. Before we open up for questions, I just want to make one observation, particularly for all the undergrads in the audience. It shows, and they've just spent a few sleepless nights submitting their major mapping reports. It shows you how important mapping is for fundamental discoveries. So it wasn't all in vain, guys, your late nighters. Do we have any questions from the audience for Maurice or Richard? And if you could just speak as loud as possible.
I thought it was all in vain.
Very sharp, very sharp.
Yeah, there we go.
Any questions? Yes, Mike.
Maurice and Richard, is there a clear indication that are there elevated levels of gold in those komatiites?
Mike, yes. In fact, there are a whole lot of, they in minor quantities, okay, but well above the cluster average and more so than any other igneous rock. But in a way, it's not really the actual gold content, it's the amount of fluid that moves through the rock and scavenges the gold to give you a economic gold quartz vein. So, it's a good question, but gold has got to come from somewhere, and for sure it wouldn't come from granite. So it's come from ultramafic rock by reworking. So that is a beautiful source rock, particularly if you alter the komatiites and you start liberating these various elements and enriching the troughs that form from them, or the pyroclasts at the top of this package of komatiites, and then you pass fluid through those, picking up gold in particular, but also acting as a source of nutrients for the origin of life. and the development of life, as is clearly shown in those biomass in the middle marker. So yeah, there's a concentrating mechanism, but it's obviously not in economic quantities at that stage. You need something to drive those fluids and to drive plenty of fluids through the system to scavenge enough to give you an economic deposit, and you need a repository of a suitable structure, an open structure where these things can be in place. So you need a competent rock, basically.
All right. Do you have any other questions? Bruce?
I'm just interested, my question is pretty predictable, I suppose. So was it Preston Cloud that discovered the first evidence of life over there, Bob?
I think he was one of the first, Bruce.
One of the first, yeah.
He was working on the gunflint flora, you know that, in the USA, which is also black turkey rock. So he read about Barberton, and that's why he came out to sample that stuff. Incidentally, in sampling it, a piece of his hammer shot off and hit Morris in the knee, and he still got it in his knee.
my knee. So, warning to everyone, if you've got a geological pick and you're hitting it with another geological pick, beware. Bits of metal can fly off and embed in your head.
Anyhow, Preston Cloud, I think, was one of the first, but again, and again, there's a lot of debate amongst these paleontologist types about whether it's a genuine organic microfossil or biomat or not. But this recent paper suggests that all the other work is a little bit not quite right, but their work in the middle marker is pretty substantial. So, you know, again, there's a lot of debate that goes on about these things and about the origin of life.
But as I understand it, Bruce, maybe you can just comment that earliest life was essentially plant life, is that right? Algae and cyanobacteria.
Well, you know, Marion would not call that plant, but it's
Well, I mean, primitive plants, put it that way.
Yeah.
And plant life is dependent on magnesium. It's the fundamental element of chlorophyll. And so you had the magnesium source in these magnesium-rich pelagiolites and komatiite rocks. So maybe there's some connection between that and the emergence of this primitive plant-type life.
Yes.
Not wanting to take away from the wonderful field work you did, do you think it would have helped your knees if you'd had satellite imagery available at the time and detailed terrain modeling?
It probably would have. You would have sat in our offices though in front of a computer screen.
Have you gone back and looked at that and just thought how that may have integrated and speeded the process into
Absolutely, you're right. Yeah.
And modern imagery you get now is phenomenal. We had 1 in 10,000 black and white aerial photographs of our mapping base, which were not bad, but I mean, there's so many good products out there now for using as a mapping base.
Just on that mapping, we had one vehicle from the CSIR. We had the CSIR bursaries, and we'd go out every day. We'd have a hell of a fight, and one guy would go in one direction, the other, and the other. The only problem was we had to get back in the evening to get into this vehicle to go back to Class, where we were stationed. Anyhow, that was just part of it. But the other part was, at one stage, we were mapping on the south bank of the Komatiite River, and the Komatiite River was in flood. And we realized that we needed to be on the other side. So there was no bridge around at all. So we saw a cattle feeding trough. And we thought, you know what, this could be a potential boat. So we got into this thing and put a few rocks there for ballast, and then set off into this current. And very soon it became kind of unstable, and it actually sank, so we were lucky to get out of it. But all the photographs with all the annotation and the mapping of 3 months went down rivers below. And so we were desperate, and eventually we started swimming and doing traverses up and down the river, which is difficult because the river was flowing quite fast. And eventually we found this old tub down on the bottom, but it hadn't moved far. And luckily for us, the photographs were on these masonite boards, and the masonite board had been pushed against the side of this feeding trough, and the current was holding it there. So we managed to salvage our aerial photograph. It was a bit full of silt and so on, but the ink, fortunately, this permanent ink hadn't run. So we salvaged all our annotated photographs, but we nearly lost the 3-month work. The hazard of field work.
Okay, I think at that point we'll save any further questions over drinks and snacks. Once again, thank you very much for that, Morris and Richard. Before you all head down, and you are very welcome to join us for drinks and snacks in the foyer of the Geoscience building after this, I just want to thank the Egoli branch for the initiation of this talk and the field trip next week. The Egoli branch is a branch of the Geological Society. So for those students in the audience, we encourage you to join the Geological Society, and by default the Egoli branch, which is a community of geoscientists in Joburg. And there'll be more talks and events like this in the future. So thank you to the Egoli branch and to all the other sponsors as well, Camera, Wits Geosciences, and Bushveld Minerals. So please join us afterwards for drinks and snacks. Thank you very much.